Welcome back, everybody. So we're going to get started with picking up where we left off in Unit 3.4 with curve sketching. I will be handing back exams at the end of class today. So I'm going to set a timer, so an hour and 40 minutes, right? Set a 1 hour and 40-minute timer. And then, so we'll make sure we spend the last 10 minutes doing that. So in the meantime, we will continue working through this stuff. So what we learned last time was that you're going to use basically everything at your disposal. You're going to find preliminary information working with the original function, then work with the first derivative to find where it's increasing and decreasing and find relative extrema, and then systematically go to the second derivative to determine concavity. So with this one right here, step 0, the preliminaries. So the domain is negative infinity to 1, negative 1 union, negative 1 to 1, union 1 to positive infinity. Because we can't have the denominator equaling 0, right? That's one of the big no-nos. One thing I'm going to do right off the bat, and I should have done it right from the start, whenever I see a rational function, if you remember from Math 126, the factored form and the unfactored form both give you important bits of information. And so I'm going to rewrite this in its factored form, which would be 3x squared over x plus 1 times x minus 1. That's why the domain is as such. And so we found the domain, the x-intercepts, if it has any, they come from setting y equal to 0, right? In the x-intercept, you set the function values, the y values equal to 0. So if I were to set this equal to 0, 3x squared over x squared minus 1 equal to 0, that will only happen ever if the numerator equals 0. So 3x squared has to equal 0, which gives me x equals 0. So I have the x-intercept 0, 0. And I'll underline that because that's an important bit of information. That's a point on my graph. Then we'll do the, oh yeah, JT.
I'm sorry. So when we're looking for the x-intercepts, we can only take from the numerator.
In this context, yes. So like in order for this expression, so what we're doing as a reminder, if we're finding an x-intercept, we're setting our function values, our y value equal to 0, and finding the corresponding x values. So 3x squared over x squared minus 1 equals 0. The only way for that to ever equal 0 is if the numerator is equal to 0. If the denominator equals 0, then you're dividing by 0, and that's that's a problem.
Okay.
Now we've already found the y-intercept technically because it's 0, 0, but let's just do it for good measure. The y-intercept, that would be f of 0, which is 0 over 0 minus 1, which is 0, which gives us the same value. We don't necessarily have to do the y-intercept since we already found it, but just in case it isn't, but this is supposed to be applicable to all situations, so we'll still show it. And so once again, with a y-intercept, you're setting x equal to 0, which means you're setting the x value, the function value, the input equal to 0. So there's where you have that. Then we got to look for any other things. Does this thing have any other interesting bits of information that you can glean from just the original function? It's a rational function. So whenever we see rational functions, they usually have asymptotes, right? Does anybody remember how to find the VAs? The vertical asymptotes? Been a while. But the vertical asymptotes, they come from where the denominator equals 0. I mean, there's more nuance to it than that, but for this course, that'll be sufficient. If it's a factor in the numerator and the denominator, you get a whole instead of a vertical asymptote, but we'll skirt by that. So we have a vertical asymptote where x plus 1 times x minus 1 equals 0, which gives us x equals 1 and negative 1 as vertical asymptotes. The other way to verify that with calculus, you take the limit as x approaches 1 from the left or 1 from the right. And same thing with negative 1 from the left and negative 1 from the right. And you'll see that this thing blows up to positive infinity at 1 or negative 1. But then HAs, you're looking at the limit as x approaches positive infinity of your function or negative infinity, right? Some functions can have two horizontal asymptotes, one on the right and one on the left. That's a very rare situation. It won't really happen very often. So it's usually sufficient to just check one direction, but we can check, you'll see that it doesn't matter in this context. So 3x squared, limit. X approaches positive infinity or negative infinity of 3x squared over x squared minus 1. And who remembers their tricks about limits at infinity? Remember, this is a limit at infinity. We're making our x values go infinitely large and either the positive, and then we should also check the negative, but you'll see that it doesn't really matter because you look at the highest degree terms. So this is equal to, and this is good practice for the final, the limit as x approaches positive infinity or negative infinity of 3x squared over x squared, because everything else doesn't matter in the face of infinity for this function. So those cancel. And you see that it doesn't, now that all the x's have canceled, there's no real need for us to worry about whether x goes to positive or negative infinity. The answer is going to be the same regardless. If we're going to positive infinity, it'll get 3 over 1. If we go to negative infinity, it'll still be 3 over 1. So that equals 3. So we have a horizontal asymptote at y equals 3. That's not step 0, that's step 1. I'm sorry. So, one more time since we were writing it down while I was explaining it. Technically speaking, we need to check the limit as x approaches positive infinity and when it approaches negative infinity. However, because of the way this is organized, that's not going to matter either way. If you just replace this with a negative infinity, it's going to give you the same answer. You can verify that if you'd like. Hopefully you can see that right off the bat. So we have a horizontal asymptote at y equals 3 and two vertical asymptotes, one at negative 1 and one at 1. Any questions so far? Yes, Jose.
Why remove -1 next to x squared?
Say again.
Why remove the -1 from x squared?
From here to here?
Yeah.
Because when we're that has to do with limits at infinity from section 1.4. If you are doing a limit at infinity, then you only look at the highest degree terms. That is step 1. We have gotten rid of all of the preliminary information that we can. We've gleaned out any x-intercepts that we can find, any y-intercept that we can have, any vertical stuff, horizontal stuff, and also the domain. Now we will move on to the first derivative. Step 2. Derivative stuff. So we've got to find the function's derivative. All right, well, f prime of x is f prime g minus g prime f. So that's 6x times x squared minus 1 minus 2x times 3x squared, all divided by x squared minus 1 squared. And because we're going to be using, so a couple things here. Notice that I use the unsimplified, the simplified version, not the factored version to find my derivative. Otherwise, I have to do way more. Right? If I use the factored version, then in addition to doing a quotient rule, I have to do a product rule inside of it, which is unnecessary. So this is all to highlight that sometimes having different formats help, and it makes more sense to use one format in terms of an operation versus another. So I'm going to use this format to find the derivative, which I found here. When I simplify this, it will become negative 6x over x squared minus 1 squared. Because you get a 6x cubed minus 6x minus the 6x cubed, the 6x cubes cancel. So we have that. And we need to find, in order to find where the function is increasing and where it's decreasing, we need to find the critical values. So we'll set the derivative equal to 0 / dne, and we will get x equals 0, 1, and -1. Which one of those is a CV and like an SCV but not a CV? Which one of those? 1 and -1. They are important values. They play a role. They're a semi-critical value. They will play a role when it comes to increasing and decreasing, but even if it goes from increasing to decreasing or decreasing to increasing, those are not going to be relative extrema because the function doesn't exist there. And so I got the 0 from the numerator equaling 0, and I got 1 -1 from the denominator equaling 0, meaning that the derivative would not exist. So we'll make our sign chart. Here's f prime's sign chart, and we'll make 3 lines because we have 3 values of interest. So -1, 0, and 1. And I'd like you guys to go ahead and fill out the sign chart using the derivative. People watching the recording as well. I'm hoping that people make the mistake that I'm thinking they'll make, but maybe you guys won't. I'm hoping you guys won't, actually, now that I think about it. Okay, so this is the sign chart you should get. You should get positive, positive, negative, negative. Now, you might have gotten something different if you didn't account for the fact that the -6 plays a role. Because the -6 is negative, it will change the sign of everything involved. So that's why I've kind of color-coded it. That negative sticks around each time, whereas and then the x is changing based on where you are on the number line. And then the denominator is always positive because it's raised to the second power. So it goes from increasing, decreasing. So at 0, and that is a critical value, that will be a maximum because it goes up and then goes down. And so I need to know where the location of that is. So I plug it into my function to find the actual location. Now we already computed it up here, but might as well just show the work in case it's not the same value. What if that was at 2 or whatever? Then you'd still have to plug it in to the original function to find the corresponding y value. So we found our maximum. There was no minimum. That's okay. And then we will move onwards. We will move on to step 3. Yes.
So we plugged it into the not simplified version, which is the same answer.
Yes. So step 3 is to find the second derivative. We use the function, then the first derivative, then the second derivative. Because all 3 of those pieces play big roles. And so, okay. This one's a very, very good one at practicing your algebra skills. So, of course, we're going to use the simplified version. Trying to use this version to find the derivative would be a very, very bad idea, because then we'd have to do a quotient rule with inside that quotient rule 2 product rules. It would not be very, very useful. So f double prime of x is f prime, so -6 times g, which is x squared minus 1 squared, minus g prime, which would be 2 times x squared minus 1 times 2x, times f, which is -6x, all divided by x squared minus 1 squared squared. Okay, couple things to think about. So first and foremost, what I'm going to notice, well, no, I don't need to notice that yet. Hopefully everyone's written it down. We can talk about what we should do. Now, it would be fine. It would work out in the long run to boil out this x squared minus 1 squared and do this distribution, but there's a faster way. Does anybody see it? Then we see something that they can do in the numerator. If you don't, that's okay, because but I want you to recognize it soon. There's a common factor that they both share. The two terms in the numerator, they both share an x squared minus 1, at least one factor of it. So I'm going to factor that out front right from the start. The reason why I'm doing that is I'm also noticing that x squared minus 1 is a factor in the denominator. So when I factor this out, I'll be able to cancel things pretty nicely. So when I do that bracket, I factored it out. So I have a negative 6 times an x squared minus 1 minus a 2 times a 2x times a negative 6x, all divided by x squared minus 1 to the 4th. And so one of the factors of x squared minus 1 will cancel. And then we just have to do a little bit of simplification. You'll get a negative 6x squared plus 6, and then you'll get a plus 24x squared. So once you take care of, oh yes, go ahead.
So we took away one of, we canceled out the top one because the denominator had the same
Factor, yeah.
How come we can't do it for the one inside brackets?
Why do you think? Because you can't.
Um,
And it has to do the fact that right here, yes, it is a factor, but it's a factor of this term. So we can't cancel, like if this was a factor of everything, then it could be factored out and canceled. But at the moment, it's part of a term. So at the end of the day, you will end up with 18x squared minus, or sorry, plus 6 divided by x squared minus 1 cubed. And remember, I want you to have the space here. Please don't write anything underneath there if you can. I know we're running low on space as it is, but the good news is this sign chart's not going to be too terrible. And the reason for that is we're going to set this thing equal to 0 to find out any, they're not critical values, but they're basically critical values. They're the critical values of the second derivative. So f double prime equal to 0 slash dne would give me x equals 1 and negative 1. That's it. And I want you to think about why. I'm getting the 1 and the negative 1 from the denominator. But the numerator, I'm claiming, doesn't give me any zeros. Why?
Because you said it's a 0.
If you set it equal to 0, it's a sum of squares. It's not a perfect sum of squares in the truest definition, right? It would have to be like x squared plus 9 to be a sum of true squares. But the thing that we know about these things is that they're never equal to 0. They have complex roots. They don't exist in the solutions are not real. They are complex. So this thing never equals 0. And in fact, is always positive. Because it's x squared, that's always going to be a number greater than or equal to 0. You plug in 0, you get 0 squared, which is 0. You plug in negative 1, you get negative 1 squared, which is positive 1, and so on and so forth. So you're taking a number that is greater than or equal to 0 and adding 6 to that, that makes this thing always positive. There's no other option for it to be. So we'll make a little baby sign chart right here. Down below. Here's f double prime sign chart. We just have negative 1 and positive 1. And we'll do some test values. X equals -2, X equals 0, and X equals 2. And so, as I said before, once again, we don't need to even bother plugging it into the numerator because it's always positive. The numerator is positive regardless. Plugging in -2, we do need to be careful in contrast to the first derivative. The first derivative had x squared minus 1 squared, which would always be positive, but this one has x squared minus 1 cubed, so that can change sign. When I plug in -2, I'll get 4 minus 3, 1 that's positive 3, so it's positive. So it's concave up here. Plugging in 0, the numerator is definitely going to be positive, but the denominator is now going to be -1 cubed because it'll be 0 squared minus 1, that's -1. Cubed is -1. So it's negative. And a positive divided by negative is a net negative. And then last but not least, if I plug in 2, it becomes positive over positive. So it's a positive. And that's a smile. Feeling positive, you got a smile. Now, concavity did change at 1 and -1. Are they inflection points? Take a second. Don't answer that question out loud. Let them get a chance to think. Concavity did change, so they could be inflection points, but are they? No, they're not. An inflection point, your function needs to be defined there. You need to be defined at the -1 and 1 in order for it to be an inflection point. So we can even add that down below if you have enough space. X equals 1 and -1 aren't inf points because f of plus or minus 1 does not exist. Okay. We have done a lot. We have done a lot here. Now we have everything. Now we can finally draw the actual equation in its full glory. So I'm going to make every 2 tick marks equal to 1 tick mark. Otherwise, this thing gets really cramped. So once we've done that, we now know where our vertical asymptotes are, where our intercepts are. So let's go ahead and plot all those things. Oh, that's why. That's why. So for the vertical axis, no. For the vertical axis, leave it as is. 1, 2, 3. Apologies. I just decided that I wanted to do it a little differently. Okay. So we have a x-intercept slash y-intercept at 0, 0. We have a vertical asymptote at -1 and at +1. And then we have a horizontal asymptote at 3. And we can label them if we want. We don't have to. And then going back through the information, there's really only one point that we ever found. If our relative maximum had been a different point, we'd plot that as well, but it ended up being the exact same point. Any questions so far?
So I don't get part what you wrote in red. X equals 1 and -1.
Aren't inflection points?
Yeah. What are
So-
inflection points?
Inflection points are places where your concavity changes. So on a graph, what that usually looks like is something like this. So when it goes from being concave up to concave down, That's an inflection point.
Um,
Or another example would be from going concave down and then switching to concave up. That point right there, it's hard to exactly determine where it is, but that's a spot where it went from bending downwards back and then went starting to bend back upwards. So that's what an inflection point is, and they come from the second derivative, and in particular, you have an inflection point as long as your function's defined there. But our function isn't defined at 1 and -1. Yes.
So we only didn't use those because in the very beginning, our domain doesn't include a positive.
That's correct. Yeah. You can, I mean, the good news is even if you forget to find the domain, you could even try to say like, oh, they are inflection points. But as soon as you try and plug them into the function, you get a math error. Like as soon as you try and plug it in here, you'll see that it like your calculator will just give you math error and you'll be done. So they like as I said, there was no extra additional points. There was no like the y-intercept and the x-intercept were the same. The relative maximum was also the same point. So there wasn't really much to plot other than just that 0.00. But on occasion, there are more. But either ways, now we've done all of that. Now we need to use our sign charts that we created along with my little cheat sheet down below to figure out what it should look like. So I'm going to put 2 lines down below. And then I'm going to plot all the numbers. So this is f prime up here, which had -1, 0, and 1. And this one's going to be f double prime, and that had -1 and 1 only. It didn't have 0. But regardless of that fact, I'm still going to split up my little inside interval everywhere. At any line, at any tick mark that I've made, I'm going to make a vertical line, regardless of whether it's part of one or the other. Because once again, the increasing and concave down looks different than increasing and concave up. Decreasing and concave down looks different than decreasing and concave up. So we have to be aware of those things, and that's why we need to make a line for every situation. What we found was it was increasing, and my little pro tip is to, like, I didn't follow it here. Try and make your arrows, your things fill out the entire segment. And then it went from concave up to concave down to concave up. Okay. Does anybody have any questions on this little sign chart? From here, we need to determine what each piece will look like. So between -1, negative infinity, and -1, how should our curve? We're increasing and we're concave up. If you're looking at at concave up, on which segment are you increasing, the left or the right? The right side. On the left side, you're decreasing, but on the right-hand side, you're increasing. So our curve is going to look like the right-hand side there. It's going to look like this. Sometimes it kind of gives it to you right off the bat. The concavity along with this stuff kind of tells you exactly what it should look like. But regardless, in between -1 and 0, we are increasing but concave down. If you're looking at concave down, which side is increasing? The left or the right-hand side of concave down?
Left.
The left-hand side. That's where your function is going to be increasing. So it should look like this. And then by a similar argument, we already looked at the graph, it'll be the other hand, the right-hand side of a concave down. And then here, you can kind of look at this to, like, this is another way you can do it. You can look at this to figure it out. You're decreasing. Which segment would you be on, the left or the right? Left. I heard people saying left, and they're absolutely correct. I caught myself. I didn't say absolutely right. You're absolutely correct. Left. like that. That gives us the overall shape of our graph. The only thing left to do really is to understand that functions, they hug their asymptotes. So as you get closer and closer to them, you should like as you get further to the left, you should start hugging your horizontal asymptote. And as you get closer to a vertical asymptote, you should start getting up and up and up towards it, or down and down, down. So with this first piece, I have to make a curve upwards. I can't go like that because I need to be able to get to here. So it should look like this. And I don't care how much it curves inwards. I've had plenty of students do this situation without going through and testing every point in existence. It's kind of hard to determine. So however you want to do it is fine, as long as it makes a curved shape. Then, based on my cheat sheet below with the pink curves, there's really only one option, that it has to come from the bottom and go up to this relative maximum, and then it has to come back down in order to match my cheat sheet. And last but not least, I have to do this. And we're all good. That's it. Any questions on that? Yes.
How do you know if it goes over or below the horizontal axis?
Excellent question. Very, very, very good question. Because, and it's Nick, correct? Yes. Nick has a very, very valid question. How do I know whether or not it goes underneath like that? Right? Because that is something that's possible with horizontal asymptotes. It is definitely plausible for a curve to do that. However, the problem is, if I were to do that, eventually I'd have to start leveling off, right? Because I can't just keep bending upwards, because otherwise I'd keep going up and past my otherwise I'd continue bending upwards. There's no way for this to I mean, there might be a weird situation where it no, never mind. That's not going to happen. Eventually, I'm going to need to stop bending upwards and start bending flat. And that would mean that I have down concavity where I don't have it. I have to be always concave up here, but based on the picture, around 3, I'm starting to concave down. Around 2 or 3, I'm starting to concave down. So that is a good thing to mention, is that unfortunately, this one, we don't get to do any fun stuff. We don't get to let our freak flag fly a little bit and channel our inner Bob Ross. So sadly, we can't do that. But if that happens on an exam, it's usually not that big of a deal. Maybe a point off, and so with a redo, half a point. Good question. Yes.
What if the horizontal asymptote was at say negative? That be possible?
So yeah, I mean, like the graph would change a little bit, but if the horizontal asymptote was down here instead at -1, the only thing that would change is that this stuff would come down with it. Based on everything that we like, if this was the exact same cheat sheet below, that's all that would change, is that everything would get lowered with it. Any other questions? Okay. We're good? We got that one and that one. Okay. So I'm going to go back to these ones for a second. These ones are some of my favorites because I don't have to do any calculations. I just get to use all the information that's given. So it says f is continuous. So sketch the graph of function f that has the following characteristic. So instead of doing all the derivative calculating, these ones are specifically dealing with all the important stuff that you find from the derivatives. So it's continuous everywhere. It has x-intercepts at -7, 2, 6, 2 and 6, and then a y-intercept at -1. The first derivative is positive on the interval from -5 to 5. It's negative on the intervals from -5 to infinity, or negative infinity to -5, and from 5 to positive infinity. You can read. I assume you can read. So in this one, we know it's continuous everywhere, so we shouldn't have any jumps, we shouldn't have any asymptotes, nothing like that. I'm going to color code this portion in, let's use purple. The intercepts. I know I have an intercept at -7 right there, at 2, and at 6. Those might play a role, they may not. And then we have a y-intercept at -1 right there. So, looking at the information on the first derivative, the way it's presented is not very helpful. Maybe you are one of those people who can handle like looking at that and immediately see that there is a relative minimum at -5 and a relative maximum at 5. Maybe you're that type of a person. That's not me. So what I'm going to do is I'm going to take those 2 bullet points worth of information. Let's use blue. And I'm going to take those things and apply them here with an F prime sign chart. So based on the information, it's not implied, it's not mentioned, but we're assuming that -5 and 5 are going to be places where the derivative probably doesn't exist or equals 0. Because those are the things that would split up my interval into those my number line into those pieces. So the only numbers in question are -5 and 5. So here's -5, here's +5. We know that in between -5 and 5, it's increasing. And then outside, it's decreasing. So there's a max at x equals 5, and there's a min at x equals -5. So we've written a lot of stuff down, so let's recap what we've done here in blue, or with the blue bullet points. We've taken the information given to divide up the interval based on the dividing values of all the interval pieces, which was just -5 and 5. For the second derivative, you see you have -2, 0, and 2. Those are going to be, there's going to be 3 values that split up the second derivative. But regardless, based on the information given, we know that the first derivative is positive on the middle piece. So it's increasing there. And on the other 2 pieces, it's decreasing. That makes 5 a relative maximum because it goes from increasing to decreasing. And it makes -5 a relative minimum because it goes from decreasing to increasing. So they didn't give us any information about 5, a point on the graph. Maybe it said that the graph has the point 5, 8. Maybe it said that the function had the point 5, 8, but it didn't. So we get to use our best judgment to make the relative maximum. We just need to make sure it's a function that does this. Similarly for -5, if it had told us that like the point -5, -8 is on the graph, then we could plot that and that would be our relative minimum. But otherwise, we get to just use whatever we want. Then we'll take this second bit of information and use that to create a sign chart for our second derivative. But this time with -2, 0, and 2. So from -infinity to -2, it's greater than 0. So on this first piece, it's concave up. And then from 0 to 2, it's also concave up. Then from -2 to 0, it's concave down. You've got that frown. And then from 2 to positive infinity, it's going to be concave down as well. Any questions on that? So I'm taking the 2 bits of information, these 2 bullet points worth of information, to create a sign chart for the second derivative. And this means that concavity changes at -2, 0, and 2, which would suggest that they are all inflection points because concavity changed and the function is continuous everywhere, which means that it exists everywhere. All inflection points, since f is continuous everywhere. Now that we have all that information, I wanted to draw these 2 sign charts on the side because it helps me identify more information. I could go straight to making a little cheat sheet down below, but I find that this helps me visualize it better personally, but I'll show you that you can just get away without doing it. And now we'll make our little cheat sheets. So here's the first derivatives one, f prime, and it had the points at 5 and -5. And then the second derivative had -2, 0, and +2. And it was decreasing, increasing, decreasing. And then it was concave up, concave down, concave up, concave down, like that. All right. Now, based, like, does anybody have any questions on how I've set up my little sign chart thingy below? Oh, I should mention that this says f prime, and this one should be f double prime. Apologies. I'd like you to fill in the middle section to figure out what the graph should look like on each segment, based on remembering that, like, which half of the smile or the frown are you on, based on whether you're increasing or decreasing. So I'm going to pause the recording. You should do that too. So this is what you should get. When you are in between -infinity and -5, you are concave up and you are decreasing. So you're on the left half side of the smile. Then between -5 and -2, you are concave up, but you're increasing, so you're the right half of the smile. Then in between -2 and 0, you are increasing but concave down. So looking at the frown, which side has the place where you're increasing? That. Then the next one, we are increasing and concave up. That's the right half of the smile. Then we are increasing but concave down between -2, between +2 and 5, which makes that shape. And last but not least, we're concave down. So based on that information, we can now start creating the graph. So we have to start off by bending downwards and decreasing. So we can make it go as shallow as we want. We could start there. We could go here. It doesn't really matter, as like, just make sure you decide. I usually recommend just drawing these with a rough sketch first with a light pencil shading, and then make it look pretty later on. So I'm going to start like this, and I'm going to keep it there, and then I'm going to erase it later on. Then, and this is another thing that some students will do, by the way, if this helps you, draw a vertical line at all of these dividing spots. So a very, very faint line. I'm going to make it this kind of dotted line here so you can see it a little bit. Can you guys see that okay? So duplicate there, duplicate there, 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 and there. These can help you out as you get started. And then you can erase them later. Honestly, I'm not going to have too much of a hissy fit about it. on the exam. Just make sure that they're very, very light. I don't want to see, like, if you're drawing this, I don't want to see them being giant black lines dividing it. It makes it a little bit too confusing as to where things are. But these things are fine enough for now. We can erase them later. So we have a minimum at -5. And so you might be tempted, based on the way my curve is going, to say, oh, well, I only have to go down here. But that's going to be probably pragmatic with the fact that that's there. I probably need to go further down. So I'm gonna go down a little bit. And then I need to start going increasing. But then at -2, I'm going to change concavity. So I'm going to have to go down like that. Then I'm going to change concavity again. I'm going to start increasing. And then I'm going to have to go up, but be bending downwards until I reach a maximum. And then I've got to continue downwards like that. That doesn't look very good right now. So I'm going to fix it. Maybe I'll have it here for reference. And I draw it the way it should look, which would be like this. So we'd go down, we go through that, and then maybe we go to here, and then we start increasing, and then we start bending down, and bending up, then going up, then going down like that. And there we have it. That's a much better looking version of the graph. And I can erase all those lines that were making it look. No. There we go. Like that. So it goes from increasing and concave up, concave down, concave up, concave down, and we're good. It doesn't need to be perfect. You can have a little bit of flair. But much like Jennifer Aniston in Office Space, you get to choose how much flair you want to put on there. Please tell me everyone here has seen Office Space. I feel like it's becoming less and less. If you haven't, who has watched Office Space? Jesus, nobody. That is your homework for this week. Please, please. It is one of the greatest movies of all time. Like it is so relatable. It has so many quotes. It's too good. You really need to watch it. It's a great thing into the eyes of corporate America. It's an amazing movie. Okay, very quotable. Any questions on that? If not, let's take a break. Let's come back at 10:02. 10:02. Okay, so we've done a little bit of stretching. We're back to it. So this next one is a little bit different. Do you notice that it has nothing to do with the first derivative? It doesn't tell us anything about the first derivative, but it does tell us a bit, some pieces of information. So it says that g is continuous everywhere except for -3 and 2. Okay, that means that as long as we keep those things in mind, everything else is well defined. It has an x-intercept and a y-intercept at 0, 0. So let's go ahead and plot that point. And we'll do that one in purple. It has no relative extrema. So there should be no hills or no valleys in our graph. That's something good to know. And then it tells us about the second derivative. We'll take care of that in a little bit. I want to, well, we can take care of it now. Yeah, why not? So taking this bit of information here, we have a sign chart that we can set up. And there's 3 different values. There's -3, 0, and 2. Those seem to be the 3 places that are causing problems. -3. Well, they're not really causing problems. They're just places that are of interest. And it was concave up, meaning the second derivative was positive for -infinity to -3. From -3 to 0 as well, it's concave up. At 0, it's concave down. Between 0 and 2, excuse me. And then from 2 to infinity, it's also concave down. And concavity changes at 0. Is 0 going to be an inflection point? Take a second. Concavity does not change at -3, so and furthermore, the function isn't continuous there, so that's not going to be an inflection point. The same thing is true at 2, but at 0, it changes concavity. It goes from positive to like concave up to concave down, and this function is continuous everywhere except for -3 and 2. So that is a place where concavity changes and exists on the function. This is an inflection point. Okay. Next, we have this information. Now, what does that tell me? The limit as x approaches negative infinity of g of x is equal to 4, and the limit as x approaches positive infinity of g of x equals -2. What does that information tell me? Because you can have a memorization of this, of what this is, right? There is a definition that has this statement in it, but you can also think about it graphically. What this is telling us is that as x gets infinitely large in the negative direction, so as we go further this way, our function values become 4. That's a horizontal asymptote. That means that your y values are leveling off at 4 as you approach negative infinity, and they're leveling off at -2 when you approach positive infinity. So the limit as x approaches negative infinity of g of x equals 4 implies HA on the left at y equals 4, and the limit as x approaches -8 of g of x equals, positive infinity, equals -2, implies that there's an HA on the right at y equals -2. So, I mean, you can draw the horizontal asymptotes throughout the entire thing. That's not wrong to do so. However, it's just going to get messy. I'll tell you that much, and you're gonna mess yourself up on figuring out which one goes where. We're saying that when we approach negative infinity, so when we're on the left half of the graph, our y values are going to approach 4. So we have a horizontal asymptote on the left at y equals 4, and similarly for the right with -2. So let's go ahead and draw those. So on the left, it was at y equals -4. And on the right, it was at -2. I realize I should probably make those in a different color. I should probably change this to purple. And then I'll change these ones to maybe orange. Yes.
Alright, so they're split down the middle because it's like this, there's a distinction of negative infinity.
And positive.
Okay, but if you just said negative infinity, or no, positive or negative,
Yes.
and it had both numbers, it'd be full one.
Yes. So if it had this, the limit as x approaches plus or minus infinity of g of x equals 4, then we would extend this line for all of it. Because it would be on the left and on the right, because as you approach negative infinity, i.e. on the left, you're approaching that value, and as you're approaching positive infinity, i.e. when you're going to the right, you're also leveling off at that value. So the direction of the infinity matters. Like the sign of the infinity does change how it looks. And then the last bit of information is we have vertical asymptotes, which I'm going to do in pink, at -3 and 2. So let's go ahead and graph those at -3 and at 2. And so unlike with the other one where we had a first derivative sign chart, this our first derivative sign chart and a second derivative sign chart, so we could set up all of it. This one we're only given the second derivative sign chart, but that should be enough. Remember, every single problem I give you in this class, there is a way to solve it. So there must be enough information, or it might not matter. But the values were -3, 0, and 2, and I'm lining them up as perfectly as I can on this problem. So this is my second derivative sign chart, and it was positive, so concave up, positive, concave up, negative, concave down, negative, concave down. Okay, so I can't really have I don't have any relative extrema, so I can't have any like any hills or valleys. So I'm kind of forced into one or two options, either this green option or this orange option. Which one should it be, green or orange? Green, because that is the piece that is concave up. The orange piece is concave down because it's bending downwards as we go from the left to the right. So it has to be the green. So let's go ahead and graph that properly. And to Nick's question before, like before, we can't do it like this. I'm going to draw that in a different color in pink. We can't do that because then that would make us have a relative minimum, which we're not allowed to have here. And furthermore, concavity changes a few times throughout here. Then the next one, do we start at the bottom or do we start at the top? The bottom, because we have to, we know. We are concave up. So we either have to come from here in purple or from here in orange. Which one would represent concave up? Because we have to eventually come down to this point, right? So either, let me use different colors than purple and orange. Let's use green. So it would either have to do this in green or would have to do this in blue. Which one should it be, green or blue? Green, because it needs to be concave up between -3 and 0. This is the blue graph is concave down. This is bending downwards. Increasing but bending down. So it's got to be the green portion. Then, do we turn back? Oh, yes, go ahead, Alex.
For your horizontal asymptotes, you can kind of trim them at, say, positive, like y equals +4, you can trim them back.
Yeah,
where it just matters when you're going to the extremes of infinity and negative infinity.
Yes, if you want to make this graph look really, really snazzy like Alex, because Alex has got amazing graphs. I've seen his exams. They're great. They're great. You can do that. You can totally do that. And that makes it a little bit more pretty, a little less intrusive. So however you want to do it. And then do we bend upwards now, or do we go up, or do we go down? Down, because we have to start becoming concave down. That. And last but not least, we either have this one in green or this one in orange. Which one should it be, green or orange? Take a sec. Someone said orange, yes. Because it has to be concave down, and the green version is concave up. So it has to look like this. And there you have it. You didn't need the first derivative. Sometimes you do. Those are pretty fun problems, right? You can just, it's really questioning, do you understand all the bits and pieces of information given to you? Once again, there's that question in Unit 3, question 10. If you haven't done this one, it really helps you, if you can do this problem, you will understand what like the graphical interpretations of all the derivatives. It's a very, very good problem. So, anyways. Yeah. With this one, do I want to spend the time or do I want to hard pass?
Yeah, I wanna try it.
Wanna try it? Yes.
The last one just for.
Oh, yeah, go back to the last one for a second. I mean, like, based on everything that I've known about you guys as a class over this last, what we are week 10 or week 9? I think week 10. Based on the last 10 weeks, I mean, like, that surprises me, JT. You guys love trig, right? Like, that's what I've been gathering. We have it all on lockdown. So that makes me think we should actually do some practice with the trig. Well, there's usually at least one. Every exam has at least one trig thing in it. And you'll skip that every single time. You'll do that one on the redo. Circle around to that one on the redo. Okay. Yeah, the square root hand thing, that's a great idea. Okay. And Parker, you're all good?
Yeah.
Okay, cool. So we'll at least get this one started, and maybe we'll find all the information, and then on the video that I post, I'll do the graph of it. You'll notice that there is no graph here, so please save some space right here for your graph to be put. I just like do a small etching. So the reason why there's no graph here is because it's very, very hard once you start involving variables like linear functions like this one has, along with a trig function. Trying to get a nice graphing grid is very, very difficult. So we will hold off on that. But we'll put a graph down there, but let's just find everything that we can. So we know the interval we're on. We're only on the interval from 0 to 2 pi. And the reason for that is that, like, I mean, this curve is really cool. And as a small note, I can show you exactly what the curve will look like. Because remember that like basically what you have is you have an x function which will increase in size indefinitely as you go from positive to negative infinity. Increase both positively and negatively. And then you have the 2 sine of x, which is a cyclic function, right? Sine x, sine only like 2 sine x will max out at 2 and min out at -2. So what these curves look like, it's actually very, very cool. This is the line y equals x. And this is what our curve will look like. Because like basically it tries to focus on the line y equals x, but that sine 2x just makes it oscillate up and down. So it's pretty cool. I mean, objectively cool, maybe not in real life cool, but I think it's kind of cool. There's another thing you can do, like there's so many fun things you can do with trig. There's so much fun in trig. But either way, we're only concerned with that one. So if we're going to do the step 1 material, which is going to be trying to find things out about the function itself, not its derivative, not its second derivative, the domain is 0 to 2 pi. X is a really, really nicely defined function. Sine is a really nicely defined function. So the domain is 0 to 2 pi. If you're going to find an x-intercept, you're setting y equal to 0 or setting the function equal to 0. It's x minus 2 sine x equals 0. That's a hard question to solve. If you remember from trig at all, when you got to trig equations, you never had a situation like this, did you? And that's because this is a very hard situation to calculate, because on one hand, you have x being a number, and then on inside the sign, you're thinking of it like an angle, and you're trying to figure out where a number is equal to the sine of an angle. And that's a very, very challenging question to find the exact value. It turns out that one of them is x, or x equals 0. Just so happens that 0 works. But the thing is, very hard to solve in general. So we'll skip. It is very, very, very difficult to find that information out. There is I forget exactly where it is, but there is an X value between 0 and 1 that ends up being true. That makes it have that solves that equation. But the way to find it by hand requires a thing probably like there's many different methods of approximation that many different mathematicians have created. Newton has his own one. That's kind of like the staple, the Newton's method of approximation. You could also use Euler's method of approximation. But those are really, really high mathematical properties that we don't even want to bother with while we're still just trying to do the basic, the bare minimum. So if you can't solve it, move on. It's not the end of the world. But we can do a y-intercept. That's the good news, is that y-intercepts are not hard to find. You just plug in 0 into the function because you want to know where it crosses the x-axis, the y-axis. 0 equals 0 minus sine of 2 sine of 0. And sine of 0 is 0. There we go. There we go. We're getting it. We're getting it. So we have a y-intercept at 0, 0. We plugged in 0 for x and we got 0 for y. So we have a y-intercept at 0, 0, which just so happens to be an x-intercept as well. One nice one to find. Otherwise, it's very, very difficult. That's basically it. There's no vertical asymptotes. There's no slope really to look for because it's not necessarily a line. So there's nothing else that we can really find. So we'll move on to step 2. And I really don't like writing, like, I really hope you can understand this as look at the function, glean whatever information you can from that, then work with its first derivative, use that for increasing and decreasing in relative extrema, and then work on the second derivative for concavity and inflection points. So that's the way I want you to work with this one. So G prime of x is equal to 1 minus 2 cosine of x. Because the derivative of sine is cosine. So, not too terrible of a first derivative, but we want to set it equal to 0 / dne. We don't really need to worry about the dne, right? Because it's not, there's no denominators, there's no weird trig functions, there's not like a tangent or secant or something. So we've just got 1 minus 2 cosine of x equaling 0, which tells us that cosine of x has to equal 1/2. Right? We'll subtract 1, we'll divide by -2. We get cosine of x equals 1/2. So we need to know what values between, what angles between 0 and 2 pi does cosine equal 1/2? Now don't say it out loud. Yes, Mark.
If you're dividing by 2, isn't it -1?
So this one always trips me up. But remember, you're subtracting 1 first, so now it's a -1. And then you're dividing by a -2, which makes it positive. All right. So 1/2, so that's going to deal with the 30, 60, 90, whether it's going to be the 30 on the, whether it's going to be the 30-degree angle or the 60-degree angle, but we want the x value to be small. So we want the bigger triangle. We want a pi over 3. And then cosine is positive in the first and fourth quadrants. So we also have, so that's pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. Not 5 pi over 5, that'd be ridiculous. Right? We all good with that one? And here's a little bypass technique. I saw JT grab his calculator. That's totally a useful thing. Just say cosine and put pi over 3, pi over 4, pi over 6, and whichever one gets you the square root of the 1/2, you know you did it right. And then just find the other ones. You don't need to have them memorized. You can use your calculator to help you out there. Say what?
I said I knew that. I don't know.
You knew that off the top of your head? I know. We all know our trig really, really well here. So I'm not worried about it at all. You shouldn't be worried. Okay. So We'll make a sign chart, but remember that we're only working from 0 to 2 pi. And here's our G prime sign chart. And then we've got pi over 3 and 2 pi over 3, 5 pi over 3. And when it comes to creating the sign chart, you're trying to pick a number between 0 and pi over 3. Now, if you want to, you can just figure out what pi over 3 is as a decimal and then find another decimal number that fits in that interval. But if you want to be super cool like all the cool kids, you need to use your angle knowledge. And what's an angle between 0 and pi over 3? Pi over 6, right in the middle. X equals pi over 6. X equals a cool angle between negative pi, between pi over 3 and 5 pi over 3. Pi over 2 works. I would have chosen pi, but pi over 2 does work. Pi over 2 totally is fine. And then one between 5 pi over 3 and 2 pi. So if you're looking at a coordinate grid, here's pi over 3, here's 2 pi. So we just need the negative pi over 6, which in terms of 0 to 2 pi, that'd be 11 pi over 6. Whoa, what did I do? This equals 11 pi over 6. Couple things here, though. Once again, it is totally fine to just plug into your calculator what 5 pi over 3 is, and then pick a number that's in between these two things, like any decimal number that you want. But key thing, and this is honestly, your calculator should not be in degree mode for this course. It should always make sure that your calculator is in radians, because we're never going to deal with degrees in this course. So if it's not in, if it's in degrees, make sure you change it. Otherwise, you're going to get wrong answers here. So we're doing it the way the cool kids do it, and we're using angles. So looking at this, if I plug in pi over 6, cosine of pi over 6 is square root 3 over 2. The 2's cancel. It's 1 minus square root 3. Is square root 3 bigger than 1 or smaller than 1? Bigger. It's bigger. So it's going to be negative here, meaning it's going to decrease. Then we can plug in pi over 2. And remember, you can just plug in, you could plug in pi over 6 into your calculator and see what sign you get. That's not a problem. You can do 1 minus 2 cosine of pi over 6. You should get negative 0.7-ish, I think. Am I right? Is it 0.7-ish? Negative 0.7? Please tell me I'm right.
The first one.
For yes, I'm awesome. Cool. All right. Then you can plug in pi over 2. Cosine of pi over 2 is 0, so it's 1 minus 0. That's positive. But you can use your calculator. And last but not least, if you plug in 11 pi over 6, you'll see that it also ends up being negative. So we have a relative minimum at, relative minimum at pi over 3 and a relative maximum at 5 pi over 3. We need to find the locations. So g of pi over 3. So the min, g of pi over 3. We're plugging it into the functions. That's going to be pi over 3 minus 2 sine of pi over 3. Now, if you plug this in, you're never going to get a nice number. The x and the sine of x aren't going to give me any nice number that I can plot. So I'm going to use an approximation. Does anybody have it calculated? So I don't have my, oh, let me just grab my calculator. Unless someone beats me to it. I forget what it is. I think it's a negative number. It's like slightly, like it's like 0.5 something. Memory serves. Pi over 3 minus 2 sine 3. Negative 0.68. So approximately negative 0.68. So we have this point pi over 3, negative 0.68. And then for a max, g of 5 pi over 3 you should get 6.96, 6.97. So 5 pi over 3, comma 6.97. All right. This 10 minutes are going to be dedicated to finding, like working on the exam redo, like talking about it and everything like that. I'm going to skip the rest of it, but I think you can kind of see how this is supposed to go. Take the second derivative, set that equal to 0. Luckily, it'll be very nice, the second derivative. So the video that I post sometime soon will have that aspect to it, along with doing this slant asymptote problem. Do not fret on an exam. I will not have a slant asymptote problem, or if I do, I will tell you how to find the slant asymptote, because that's something that's everyone forgets about it for whatever reason. I don't know why. It's such a useful property that we use in everyday life, right? Giovanni, have you used slant asymptotes when you go to the target, right? Yeah. See, I told you, super useful. So I don't know why we don't have them memorized. But anyways, I'll get that posted sometime soon. Okay. Everyone's second favorite topic in all of Math Calc 1, which is optimization. It's word problems, part 2. So I am a generous God, right? Because I don't put related rates and optimization on the same exam. Because a lot of students get confused which one's which, because they have different procedures. But I want to mention 2 things. First and foremost, remember, the final exam is cumulative. And I will tell you this, I will be this honest with you on it. On the exam, on the final exam, I would not be surprised to see at least one. There's either going to be an optimization problem or a related rates problem. However, yes, go ahead. Yes.
Not both, one or the other, or potentially both.
So, like every single time I've taught calculus in the past, the department has and so the thing is, the departmental final is the bare bones, and they suggest that you add a few extra problems. So I usually add on my own ones, and depending on how the Seahawks do this year, there might be one of both. Now, the good news is, though, it is not too terrible to figure out which is which. The key thing is in the verbiage. An optimization problem has words like maximize, minimize, optimize, biggest, largest, smallest, all things that you're trying to quantify a largest or a smallest value. You're trying to maximize or minimize something. That has to do with optimization. Whereas related rates problems always involve find the rate at which blah happens, find the rate of change of blah. There's a big difference in the verbiage. So if it talks about trying to find the maximum of something, we're talking about an optimization problem. So you'll see that once we look at this problem, and then I'll try and show some analogs to Unit 2's related rates. But I do want you to be aware, like a lot of the times, the last 4 times I've taught Calc 1, it's usually been that there's at least one on there. I think one year had both. And then every subsequent year, I usually add one of each, just so that we get that practice in both of them, though I might change my mind on that fact. Anyways, so read the problem carefully. Make sure you take time to digest all the important details. So, but as I just said, in optimization problems, the keywords to look out for are optimization. You're looking for words like maximum / minimum / optimize / largest / biggest, etc. That's how you can tell it's an optimization problem. If it says in a problem, it's you want to find its largest size, or find when the volume is at a minimum. That means it's optimization. You're trying to optimize a problem. That's what it means to optimize. Whereas related rates have things like rate of change slash changing at a quote unquote rate, etc. Because remember, a rate is a fraction. It is a unit of measurement over a different unit, or a unit of interest over another unit of interest. That's what a rate is. Usually dealing with time. So like feet per second, or miles per hour, or cubic centimeters per nanosecond, or whatever it may be. But that's the way you distinguish between the two of them. Step one or step zero, that is step one. Yeah. Draw a picture if possible. As per usual, you'll be surprised at how much information a picture can help you visualize. Then what you're going to do is write down any relevant information that you have. Unlike with related rates where it's a know and a want situation, this usually ends up having two different equations. You usually have what I like to call an optimizing equation. The optimizing equation. So this involves the quantity you want to optimize. Optimize, not optimize. That's ridiculous. So you usually have two different things. One of them is the optimizing equation you've created. So imagine, like, as an example, we'll see some things in the future, but like, imagine the question saying, find the dimensions that create the maximum area of a rectangle. Then the area is equal to length times width. That would be your optimizing equation because it's trying to maximize your area. Or maybe it's saying find the minimum perimeter, and you have P equals blah 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 blah. P is trying to be minimized, so that's why you're using that situation. It involves the quantities you want to optimize, and you sometimes this will have 2+ variables. If so, you'll need to substitute using the below equation. An optimizing equation, and then sometimes you have multiple different variables. And seeing as this is calculus in a single variable, we haven't talked about multivariable functions yet. There's not really any way for us to take derivatives of multivariable functions. And you might be wondering, why are we talking about derivatives? Well, how are you going to try and figure out where you have a maximum or a minimum? You need to know the derivatives so you can use the first derivative test or the second derivative test. So if you have multiple variables that are true variables, they're varying, then you can't take the derivative yet, so you have to have what I call a constraint equation. Or a limiting equation, any word that means the same thing as a constraint. It is a requirement on the variables. And you'll see one in action in just a second. This usually involves a quote unquote bound, which will allow you to write one variable in terms of the others. For substitution. Okay. So sometimes you don't have a constraint equation. Sometimes it's just an optimized equation, you're done. That'll happen on a couple of problems that I've created for this lecture, for this section. Other times, there will be something where your optimized equation will have multiple variables, and you'll need to find some way to get around that. And that's what the constraint equation will do. It'll probably provide a bound on these types of things that allows you to solve for one variable or multiple variables in terms of the others for substitution purposes. So if you have a constraint equation, use it to make a substitution into the optimizing equation to create a function of one variable. We like this. We can work with this. Later on in Calc 3, you will learn how to deal with a multivariable function. But right now we can't do that. And this actually, if you're wondering, there is a more complicated version of this. I don't mean more complicated as in more difficult, but it revolves around more variables. There is a nice analog to 3 dimensions and beyond, and in fact, more than 3 dimensions, sort of like meaning more than 3 variables, which is called Lagrange multipliers. Lagrange multipliers are a very, very common tactic to try and optimize things. So you will see that in Math 283 hypothetically. If not, you'll see it up further, like later on math courses. But either way, we're just going to deal with optimization for now. Then what you're going to do is you're going to optimize the function by taking its derivative and finding critical values. Be careful about your domain because sometimes you will find critical values that are outside of the scope of the problem. And we'll see that in a second. And then make sure you test the endpoints if you're on a closed interval because of the extreme value theorem. Because of extreme value theorem. Unit 3.1. And then be sure that you verify that it's a maximum or a minimum. You do need to verify. I will mark down otherwise. I don't want any of my students going on to become civil engineers and not verify that the structural integrity of their bridge is at a minimum when it should be at a maximum. And then we have a bridge that collapses. I don't want to be blamed for that. Because you know what's going to happen. You're going to like, they're going to get all in your case and you're going to say, blame my Calc 1 teacher. He didn't show me that. Now I am in for a lawsuit. I don't want that. And so this way, now that I have it here, now if that does come to light, I will show them this page of our document and say, no, I showed them. And then it'll be back on you. And then last thing is to answer the question completely. So maybe the question's asking for the maximum area, but you found the dimensions. So you need to multiply your dimensions to find your area. Well, we'll get there. All right. For whatever reason, my timer stopped with 5 minutes. So like because we have 10 minutes, which is where it was supposed to stop. We will let's call it good for today. We'll pick up next time and do this. The quiz on Wednesday will cover 3.3 and 3.4. So curve like finding all the information you need to know about a function pretty much. Okay. So I'm gonna hand back the exams. I also have some quizzes to hand back, but all right, Alex, Eduardo, Alexis, which one, Eduardo? You have the little ones, yeah. See, that's the one that's I wanted I was like for sure I got this one. I think I've got Valerie. Valerie. So sorry. Young. Damn it. Yeah. Yeah, I was just I was leaving.
Hey, she goes online.
James. James. Yeah, that's what I, one of the 5-point quiz.
Okay.
Here. John. Eric.
Saw you. Wait, would you put the one?
JT.
Which one?
Giovanni.
This one? Graphic.
Here.
Oh,
Lexi. So, overall, is the recording still going? Overall performance was really good. I was like, especially, sorry, specifically, I was thinking about question 10. People did really well on that one. I was super pleased, and that's not usually been the case for me. And also on question 12, I was very pleased with how much work you guys were showing for the last part. That problem is very tricky. I threw that one in there. It was only worth 3 points, but I tried to be as generous as I could with those ones. The answer was only worth 1 point. Any work was around 2 points. So, anyways, and remember, there's an option A and an option B for questions 4 and 6, right? Who's gonna ask it?
Are we getting it as extra credit?
There we go. There we go. Thank Erica and thank JT. Each for questions 4 and question 6. If you do the other option, I will make it worth 1 point of extra credit. So that's 2 points that you can add on top of your exam score. So do both of those derivatives and you get extra 2 points on your exam score. What else was I going to mention? I think that's about it. Yeah. If you guys, as per usual, please make sure that everything lines up correctly, both on each page, and make sure that the score has been correctly transferred to the bottom, and then make sure that score has been correctly transferred to the front. Make sure there's no calculation errors, and as long as that's good, keep working through it. Otherwise, and you guys know the deal at this point. Should only be you working on this. You can always contact me for help. I'm happy to do any of that stuff and help give you guidance. There should always be at least one problem in our notes that can help you figure out these types of problems. But otherwise, I also have some quizzes that I can hand back, but so that I can start making this become less massive. But yeah, if you think you got ungraded unfairly on anything, please feel free to ask me. Otherwise, we'll do it. We'll see it. It'll be due next Monday. Okay.